Welcome back to functions. I have started with pictures of 4 different relations, and maybe on this one on the left, I think there might be a glare, so I will write the ordered pairs below. Let's call this this one F. I get an F, G, H, and maybe J. For relations, I should say. They're not all functions. We will remind ourselves about this. This one, as I said, I think there's a glare when I was looking through the camera, so let us write the ordered pairs. A relates to 2, B relates to 3, and C relates to 1. Oops, open parenthesis. And you could do that for any of them. We discussed this both in class and also briefly in the last video, how you go from a picture like this to a set of ordered pairs. The arrow means that the one over here relates to the one over here. And all of these are relations from subset A to some set B. Now, let's go through and think about what we were discussing with functions and see if we can remember from last time. This one, not a function, okay? So G is not a function. Because the set of first coordinates in ordered pairs is not all of A. So you could write it as this, that B is not in the set of all first coordinates of ordered pairs, x such that x comma y is in G for some y in B. And because this little b is not in this set, we know this set is not all of A. That was our first condition for being a function. But this is not a function, okay? Well, J is the other one that is not a function. J is not a function. And the reason here is because of the second condition. So here A relates to 1 and A relates to 2, but 1 is not equal to 2. Or I could have written this in terms of ordered pairs, right? But this is the second condition. Now, H and F, these are both functions. H is a function, F is a function. Maybe I need some lines here to separate where I'm just talking about these. This is a function, and what we discussed last time was this concept of 1 to 1. This is 1 to 1. We do not see 2 coming into the same. So if we started over here, we would, this one, not 1 to 1. We have 2 going into the same one. Over here, we're fine. 1 to 1. 1 to 1. F is a 1 to 1 function. F is a 1 to 1 function. Because if f of x equals f of y, then x equals y. H is a function, not 1 to 1. But it's not 1 to 1. Sometimes it's written this way, or 1 dash 1. Maybe I'll just write it 1 to 1 as, okay, H of A equals H of C equals 1, but A is not equal to C. That's our justification. Okay, so this was to refresh our memory of the kinds of things we discussed last time. And now we will move on to the concept of onto. But I will repeat that, and we'll practice this some even today, that it's important to understand being one-to-one is an implication. Okay, you have an implication, and that would be how you would, for example, start a proof of something being one-to-one. We did one, and it was a little not too terribly hard of a function to work with. We will work with more today. Okay. So now we will define definition f from A to B. Remember, if I write this, what does this even mean? It means f is a function, the domain of f is A, and the image is a subset of B. Okay. Is onto, provided, well, you can say it shortly or succinctly like this, that the image of f is B, but this is not necessarily the best way to work with the concept of onto for proof. So let's unravel what this means. We know the image is always a subset, right? So what this means in terms of if you want to prove something is onto, I'll say equivalently, this is what I personally would use. It says for all B and B, there exists A and A with f of A equals B. This says that the set of all second coordinates in the relation, it fills out all of B. So there is some A, such that A relates to B for any B. Okay, so, well, maybe before I do anything else, let's talk about what it means to be not onto, and then we will look at the concept of both one-to-one and onto for certain functions. Or maybe I'll go back and do some of the functions that we decided whether or not they were one-to-one, and we will figure out if they're onto. Okay, so to be not onto. Again, this is practicing a negation in a way. We have to negate this. It means that this statement here written in blue is not true. Or, well, here, it says that the image of f is not equal to B, right? That's negating this. But here's a way that I have it in terms of a proposition with quantifiers and things like this. So I can negate that saying there exists a B in B, such that for all A in A, f of A is not equal to B. So you have to find, and that would be the same way you think about it if you say that the image, maybe I'll write that, not equal to B, like this, but we know that it's like this if I draw a Venn diagram. We know B is like this, and the image sits inside. So here's B in this little bitty circle, or maybe it's larger, but my picture is small. The image sits inside B. That's the image of f. So you have something here that's not in the image, right? That would say that they're not equal. And that's written like this. Well, if I go back to, and they're erased, but I will just draw one example of how you spot something is onto or not. 1, 2, 3, 4. If I would have had a big enough board to leave those up, I would have just referred back to the ones that I had. If this is A and this is B, first of all, I need to be a function, and so I need to make sure I have only one arrow coming out of every single one here. So if I assign here 4 relates to 7, or f of 4 equals 7, this is an onto function because every element over in B is in the image, or there is an A that relates to it. And you can see here by looking here at the arrows. So this is onto. It's not one-to-one if we go back and think about that concept, because f of 2 and f of 1 are both 5. 2 is not equal to 1. But it's onto. Okay? Now, I'm just going to change the same picture. So now let's erase this. and erase this. Okay, I can define f of 4 differently to where I am no longer onto. Well, just take f of 4 to be 6. And now this is not onto, as 7 is in B, but 7 is not in the image of F. Okay, so this is not onto. So you see this concept of being onto or not onto by if you fill out all of B with arrows hitting the elements. This is onto. Okay? Now, which functions did we work with last time? And let's go back and look. I need to back up in my notes. Pardon me for a moment. Here's one. The first example we'll do is F, which went from R to Z. Well, we did G. We did the ceiling. So let's do the ceiling, where G of X is the ceiling of X. Okay, round up. The question is this onto? Yes, this is onto. Now let's prove it. This actually isn't that hard to prove, but you always must think about the function. Okay, but here comes the question, how do you start a proof of something being onto? Well, you must take an element, I'll even maybe call it B, in the codomain. And then, right, you need to find this. No. Here, I was going to say, wait. We're trying to show it's onto. I pointed to the wrong thing. Right, you need to take something in B, because this is a for all, and then, based on this, find something in A such that f of A is B. So we need to find A in R with f of A is this particular integer B, okay? And that's exactly how you would prove a statement of this type. So maybe I did this for one-to-one, I will do this for onto, I box it, I star it. You always want to start a proof by onto like this. You start with something in the codomain, and then your whole goal, well, you have to think about the function, but your whole goal is to find something in the domain. One element. You could find 15, it's not going to change anything. You only need one. That maps to it, and then you know onto. Okay, well here, B is an integer. In particular, B itself is an element of R. So we can say, notice that B itself is an element of R, and if you take the ceiling of something that's already an integer, you get this, because that's the way the ceiling works if you're already an integer. So we have, or I should have said G of B, right, equals, well, you take the ceiling and you get this element, so thus G is onto. Now I could have also, I didn't have to take, well, I'll put this because I have finished. I've shown it's onto. I didn't have to take this because we know there are many different things that map to this one integer. I could have just the same done here. I could have said B minus 0.1. This is an R. You take an integer, you minus, well, that's definitely a real number. You get a real number. And if you take the ceiling of that, then you get B, because this would be, well, it'd be B minus 1.9. Take the ceiling, you get B. That would be another element that would map to B. But you don't need to find multiple ones just to prove a function is onto. You only need to find one. And so I will erase this because that was just a comment, and it's not necessary part of the proof. Okay, so this is the proof of this being onto. Let's see, what other function did we look at last time that I want to say something about? we had 2 times the absolute value of x. Let's do that one, and then we will do the one that went from non-negative integers cross non-negative integers. Okay, so then I'm going back to a few of the examples that we looked at with 1, 2, 1, and I am figuring out if they're onto and then justifying it either with a proof or justification as to why not. This was a proof that it is. Okay. So the next one that we will look at was f from z to z. F of x is f went from, so example, f went from z to z, defined by f of x is 2 times absolute value of x. Okay, well, hopefully you can, we already discussed the image, right? That was part of our exercise. And we found that it only consists of 0, 2, 4, 6, etc. So we could use that argument here that we found the image as a set and that was not equal to z. Another way you can just do it is find one element, and that was that there exists thing that I erased. Find one element here. So notice -1 is in z, okay? But -1 is not in the image of f as, well, absolute value of x is always greater than or equal to 0, and 2 is greater than 0 means 2 absolute value of x must be greater than or equal to 0. Something like this. Thus, the image of f is not equal to z. You could also, and maybe it would have been easier, just to write out what the image is. We did that last time, and then say that it's not z. This is another way. There's always multiple ways to go about it, but this way, and one reason I did it this way is it illustrates you really just need to find one element that's over here in your codomain that is not in the image. Then you know it's not onto. Okay. Now the final one that I want to do now, in terms of either a proof or justifying why it's not onto, was we had the function that went from non-negative integers cross non-negative integers into integers. So let me do that now. We have, let's say, A, if you recall, was n union 0, and then I called it, did I call it F or G? I guess it doesn't matter. It's a new video. I can call it a new thing. I will call it F, I suppose. F goes from n cross n into Z, where F of M, N, oh no, not N, excuse me, A, okay, equals M minus N. And the question is F onto? We showed it's already not 1 to 1. That was in the last video. Is it onto? Well, here's where you really need to think about the function, because it's sort of prove or disprove. F is onto. In this case, we will prove it. I'm going to claim F is onto. But you have to be a little bit careful, because you can't just say, well, I'm just going to do M0 or something like this. That would not fill out all of the integers, because we're only sticking in non-negative things here. So I like this example because we really have to think about how proofs of being onto go. Okay, so proof. We always start the same as I did in the last example. We let's say, B in Z, in the codomain. And then we want to show B is in the image. Okay, I'll just write it that way here. Show B is in the image of F. Well, so I have something in Z. This is what I was saying. If you have B and Z, you can't just do B0. You know F of B0 is B. But that only works for non-negative things. So this suggests we should break this into cases because you know every integer is positive, negative, or 0. So case 1, is that B is greater than or equal to 0, okay? Now I need to create something that maps to B. This is the one I was mentioning. Then, if B is greater than or equal to 0, B0 is in A cross A, and F of B0 is B minus 0, which is B, okay? So if we're in this case, I have found an element that maps to B, so I'm finished. This is what I needed. Comma, meaning B is in the image. Okay, now case 2, we have to think a little bit. We might have B negative because we need to show that all of the integers are equal to the image. And here, we can almost do the same thing, except we have to do a little trick. So then, if B is negative minus B, this will be positive. This would be in A. Oh, yeah, that's fine, in A. And 0, comma, minus B will be in A cross A. So this is going to be my element, as we will verify. So we have F of 0 minus B is, okay? Well, it's this minus this. 0 minus B, which is B. Again, meaning B is in the image. And we are finished. We've shown F is onto because in either case, we showed exactly what we needed to. We started with an element of Z. We showed it's in the image. This is an onto function. Let's do one more example, and then I will define bijection here. This is going to be an example that was not from last time, but we will look at both one-to-one and onto. Let's define F, from, let's take real numbers minus 0. This is my set A into the set 1 and minus 1, where F of some real number that's non-zero is x divided by the absolute value of x. So maybe before I say anything, you can think about this. Why is it mapping into 1 minus 1? What's F of 2? Well, 1. What's F of minus 2? It'd be minus 2 over 2. It's 1, negative 1. Okay? What you see here is this is the SIGN function. And what do we know about this function? So my claim, F is not 1-to-1, and F is onto. Maybe I should label these. This will be A, and this will be B. This will be A and B. Well, neither of these are too hard to see. For F not being 1-to-1, for A, we can just notice we need to find two real numbers that are not 0, that have the same SIGN, sign, they're both positive or they're both negative. So we can just say, notice 3 and 5 are in R minus 0. Maybe I'll put parentheses like this. And if we take f of 3, this equals f of 5, which equals 1. But 3 not equal to 5. Not 1 to 1. Now how is it onto? This one is not going to be an abstract proof. We're not going to say let B and B and then find the A and A such that, or you could, but there's only 2 elements here. So to verify that every element gets hit, you just find something that maps to 1, find something that maps to minus 1. Okay? So notice here to prove that it's onto, well, we have it here, f of 3 equals 1, and f of, let's say, minus 7 thus, well, f is onto. Okay, we just had to, this one, as I mentioned, rather than working abstractly, because our codomain only had 2 elements, we just find something that maps to each one. And it looks almost like a calculation, but this is a proof that f is onto. Okay, very nice. Now, we have one really important definition now, and that is of a bijection. Definition, f from A to B is a bijection provided f is 1 to 1 and onto. So we need both of these. Okay. Then we have a bijection. If you are both, well, this is not a bijection. The last one was not a bijection. We had it was onto, not 1 to 1, where we went from non-negative integers cross non-negative integers into integers, where you took f of mn is m minus n. Not a bijection. So here's something really interesting to think about. This will be, we will fill the board with more signs. We have a sign, let's do the other sign. So let's look at f of x equals the sine of x. Now, if it's been a while since you've thought about trigonometry, it's okay, I'll graph it and we can think about these concepts. This is periodic with period 2 pi. 3 pi, 4 pi, like this. And then there's here and here. And the sign, well, it always goes between 1 and minus 1. But the sign goes, maybe I'll graph it in green. The sine function, SIN, or SINE, is 0, high, 0, low, 0, 0, high, 0, low, 0, like this. And it continues like this. Okay, period 2 pi. This is f of x is the sine of x. Okay? Well, if we consider f mapping from R to R, this function, or what about if we consider f mapping from R into the interval minus 1 to 1? Or what if we consider f, I will do here, okay, f, the same function, what I'm doing in this exercise, I'm taking the same formula and I'm thinking about what happens if I switch the domain or the codomain, okay? But I'm still taking the exact same formula. I'm taking, in terms of a relation, I'm taking the ordered pairs that you see on the graph. You just might have to cut down to a certain part. And I'm either considering them, here I would consider the whole R, and then I would consider the relation as being on R in this component. Relation from R to R, this would be considering it as a relation from R to minus 1, 1, etc., like this. Okay? So now let's consider the same function or the same relation. I'm just changing around things. Now let's think about if we restrict the domain to, say, pi over 2 to 3 pi over 2. To r, and then finally I will restrict both. I will consider this as pi over 2 to 3 pi over 2 to minus 1, 1. Okay? I like this activity because you can see that if you change what you are considering to be the domain, so moving from this column to this column is thinking about restricting the domain. Or if you think about changing what you put as the codomain, it changes whether the function is 1 to 1 or on 2, or bijection, which is really why when we mention all of these concepts, it's not about some underlying function. It's really always a function together with an A and a B. And then you can answer the concepts of 1 to 1, on 2, or even being a function for that matter. Okay, so these are all, with these all listed, we have functions. Okay. But now, if you consider the whole real line and the whole real line, it's not either one, because remember we were talking last time about this horizontal line test is not 1 to 1. So this one is neither 1 to 1 nor on 2. Nor on 2. Okay. It's not on 2 because, for example, 5 is not in the image, but 5 is a real number. 5 is way up here. Okay, you see looking at the graph, or when sometimes I have taught classes where you're looking at a graph, trying to figure out the domain and the range, I think about squashing it to the x-axis. This gives the domain. You squash to the y-axis. This gives the image. Okay, but here, now, let's consider r to minus 1, 1. So we do, in fact, fill up all of minus 1, 1. This one is onto, but not 1 to 1. The image, without a doubt, is all of minus 1 to 1. In fact, you might have thought about the inverse sine function, the arc sine, right, has this as the domain. So this is on 2, but again, because we're on R, fails the horizontal line test, not 1 to 1. Okay, come over here. And this one, well, if I restrict my domain, and here, I'm starting here to here, this, on the red, you notice I do pass the horizontal line test. So this one here is 1 to 1. Oh, you might not be able to see over there. Maybe I'll write it above. I had these, I don't want to go off of the screen. So this one is 1 to 1, but it's still, it's not on 2, not on 2. I'll write that above also. Not on 2. And finally, this is the really nice one. Well, it's nice in terms of being a bijection, where you are 1 to 1 and you are on 2. Okay, so this is a bijection. We found one. Because if you restrict the domain here and you only look at the interval minus 1 to 1, then you are both 1 to 1 and on 2. Let's do another example of a function that's a little bit more complicated in the concepts of 1 to 1 and on 2. So let's consider H, which will map Z cross Z into Q, the rational numbers, defined as follows. Let's say H of M is equal to, it'll be M over absolute value N plus 1. Okay? And this is, Well, this is definitely a function that maps into Q because typically when you are dividing, you have to worry about 0, but you're never going to have a denominator being 0 here because we have absolute value. It's always greater than or equal to 0 and then plus 1. Okay, let me get this other marker. Okay, that one is good. So let us, over here, we will prove or disprove that H is onto, and then over here, maybe let's do 1-to-1 first. Excuse me, that'll be a little easier, I think, and you might see that already. We will start with H's 1-to-1. And then over here we will prove or disprove that H is onto. Well, what I was saying just a moment ago that you might see the case here immediately, you can think about rational numbers. When do you know a rational number is 0 or a fraction is 0? Well, it's 0 only when the numerator is, so 0, 4 and 0, 7. Those go to the same thing. But also another way you could think about this function immediately and see that it's a disprove that H is 1-to-1 is we're sending in numbers that are integers or pairs of integers really, but anytime you see an absolute value coming, it's somewhere in your function where you can put in both positive and negative potentially. That's a pretty good sign it's not going to be 1-to-1. Okay, so here we go. This is a disprove, and I will use two different ones that have 0 in the numerator. I'll just say consider 0, 4 and 0, 11. Doesn't really matter. These are both in Z cross Z. Okay, two different elements of Z cross Z. And then we have H of 0, 4. Well, this is 0 over 5, which is 0. And H of 0, 11. This is 0 over 11 plus 1, which is 0. Okay, but 0, 4 not equal to 0, 11. Oops. And so you see this is a justification for why this function is not 1-to-1. You could have many other examples, but this is one. We have two different elements that map to the same thing. Okay, now what about here, H being onto? This, in fact, is onto, and this might be a little tricky to think about, but it's good to do this one. How do we prove something is onto? This will be a proof. Well, we always start the same, as I mentioned. Take an element, let's say B in Q. Okay, you always take something over here in the codomain, and then we must find an element in the domain that maps to it. Well, I'm going to have to use what I know about rational numbers. In particular, I'm going to use this idea that if you worked on this problem from the last section, they're really equivalence classes. I hope you did think about this problem, and we can pick representatives. Well, okay, what does that mean here? I'll just say this. Then we may find let's say X, Y, and Z with Y bigger than or equal to 1 and B equals X over Y. The rational numbers as a set is just that you could find X, Y, and Z with Y not equal to 0 and B is X over Y, but really there are a lot of fractions that are equal. You could always take the denominator to be an integer bigger than or equal to 1. And if it happens to be a negative number, the negative would just be absorbed in the X in the top. And you'll see why I want to do this in a minute. Okay, so let's say y bigger than or equal to 1, then we know that y minus 1 is bigger than or equal to 0, meaning that the absolute value of y minus 1 equals y minus 1. That's what I know for non-negative numbers. Okay, now I have everything ready to find my element in z cross z that maps to this little b. Okay, so consider my element will just be x, comma, y minus 1 in z cross z. And then h of x comma y minus 1, well, the definition of h is that it's x over absolute value y minus 1 plus 1. But the whole reason I found this representation of b with a positive y in the denominator is so that I could take this next step, which I have already justified, that this equals here, and this is x over y. And, well, maybe I should say one more thing, and I'll do it here. X over y was our b that we started with, so thus h of x comma y minus 1 is this b. And this is what we needed to show something is onto. You pick an arbitrary element here in the codomain, and then you must, depending on the function, right, you have to think about the function, but depending on the function, you construct something over here in the domain that maps to it. And that's one reason I really like this function and this problem, because you really have to think about the function to construct this in the domain that maps to it. Okay, well, comma, I'll finish, meaning h is onto. Okay, and that finishes this. Now let me I would like to prove something. Okay, so let me erase. What I'd like to prove is something that we have definitely discussed in video 1, and it's something that the proof will be very short for us now. So it's something discussed in video 1 about a function and its inverse. Now that we have this concept of bijection, that means you are one-to-one and onto, then I can state it in terms of that. We will discuss why it's the case. Okay. Okay. It's not quite dry. One more. Maybe I'll get these. I will spray a little bit less next time to erase. Okay, so the theorem is, and this is quite an important one. So we have A and B. We will let A and B be sets. Okay? And we will have some function. F goes from A to B. Okay, well, this theorem says that F is a bijection if and only if the inverse relation F inverse is a function from B to A. Now, part of this is what I was mentioning when I started to erase, part of this we have discussed. This came up in video number 1. And maybe I will remind you that in the proof, we've discussed part of it, which is when F is 1-to-1, the inverse relation is a function, but there's a little bit more here. So let's talk about the proof. Okay, now, typically, and Well, you know, I like to always, just to save myself from making a mistake, I will do an if and only if in two directions. So for example, I would assume f is a bijection, prove the inverse relation is a function from B to A. Then I would assume this part and then prove f is a bijection. But this one, I'm going to just prove all at once with a bunch of if and only ifs. Okay. So let's begin. F is a bijection. If and only if. You know what? Maybe let's do this, have a little more fun with this now that I'm thinking. And I will make all my if and only ifs blue because I like color. Okay, F is a bijection. If and only if. Well, the definition of bijection is that F is 1 to 1. And F is on 2. Well, now let's unravel these. This is an and, right? So let's unravel this. F is 1 to 1. This we discussed last time, but I'll do it briefly, if and only if. Well, what does it mean? It means if you take, let's say, AC in F and, maybe I should call that B, AB in F and CB in F implies that A equals C. Okay? And this is the case. So this holds. Or I should say this is equivalent, or this holds if and only if for F inverse, move it up here. For F inverse, we have, and now just like I did in the last video, we translate this statement into F inverse. This says BA in F inverse and BC in F inverse implies, well, the same implication, A equals C. Okay? So now, this is the definition of function, right? Or it was one part, okay? So, if and only if, or this is equivalent to, maybe I will do if and only if. If and only if F inverse is a function. And when it's a function, well, we know what the domain and the codomain would be because they're the set of first coordinates for F inverse, this is the domain. The set of second coordinates for F inverse, this is the codomain. But this isn't just any relation, it's F inverse, which means you interchange the two coordinates coming from F. Okay, so maybe let's put some words down. So where the domain of F inverse, this is the set of first coordinates. This is the image of F, just by definition, okay? Because the set of first coordinates of F inverse is the set of second coordinates for F. And the image of F inverse is equal to the domain of F, and we know this is A. Okay. Okay, now let's put a second bullet. Because this is a bijection, if and only if two things happen, and we have discussed the consequence of the first thing happening, which is the second time we discussed it, but it's fine. It's good to remind ourselves why it's the case. Now, okay, F is onto, this one's a little shorter, but F is onto, if and only if, the image of F is B. Okay, and this would say, if and only if Well, we know the image of f is the domain of f inverse. The domain, this is again, we interchange equals b. We interchange, this is the second coordinates of f, will become the first coordinates of f inverse, or first coordinates of ordered pairs in the relation. This is what I mean when I say that. Okay, so now let's put this all together. All together, I want to be using my black marker here. All together, we see f is a bijection if and only if and only if f inverse, well, the domain of f inverse is b. Here it says the image of f inverse is a function. And this is exactly what the theorem says. Okay. Let's do a quick example, and then I'm going to make a statement. Let's have A here. Well, suppose, let me state this. Suppose cardinality of A is 3 and cardinality of B is 4. So it's something like this. A, B, 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, maybe 5, 6, 7, 8. Here's A and here's B. And I have a question, and then I will turn this around. Let's flip them. Suppose the cardinality of A is 4 and cardinality of B is 3. And the question, well, again, I better leave room for that question. I will put them here. 1, 2, 3, 4. 1, 2, 3. Here's A and here's B. 1, 2, 3, 4, and maybe 8, 9, 10. Okay, doesn't matter. My question is, for both of these, maybe I will put the question in blue in the center. Okay, this is going to be nice. Here's my question in both examples is, can I have a bijection? F from A to B. Question mark. And this is in each case we have two different things to address. Okay? Well, we know bijection, we must be 1, 2, 1, we must be onto. So let's just try and see what happens. Okay? So first of all, I have to be a function first, right? So I can only I have to include all of these, and I can only put one arrow. Here I go. I just start assigning, trying. I need to keep 1 to 1, and then, well, what's going to fail in this case? I'm just trying to make a bijection. The problem is, so in this case, the answer is no. Let's say this is F. F cannot be on 2. You see that here, okay? Because even if I had had a different choice of f of 1, f of 2, and f of 3, whatever's left over, there's no way that this can be hit, okay? So the problem is I don't have another element over here to go there, okay? The answer is no. With this cardinality and this cardinality, you cannot have an onto function. Now let's look over here. Well, okay, no problem. Start trying to make something both 1 to 1 and onto. I assign here, and then maybe I assign this here. Well, I have to stop adding arrows. Well, I have two choices. either I leave 3 out of the set of first coordinates of the relation, which makes it not a function from A to B, or maybe I'll call that F also. Or I assign 3 somewhere, pick a place, right here. And that would be a second arrow that goes into 9. And then I would have that it is not 1-to-1. So here, the answer is no, if in fact you do have a function that you cannot, I'll say it this way, be a 1-to-1 function. And this argument works in general. We will see more of this kind of thing later, something called pigeonhole principle. But I like to think about it now when I first introduced the concept of bijection. It is in fact the case, and we will get to this later. It's a fact. And you can probably even guess it. Maybe I'll call it theorem, because we'll get to it later. Theorem. You can probably guess it just by seeing this example is that if you have F from A to B is a bijection, and I'll state it this way for now with A and B finite sets, then you must have that the cardinality of A equals cardinality of B. And this is something we will come to a little bit later. Really is pigeonhole principle. So if you have some bijection between 2 finite sets, they must have the same cardinality. But the idea is really exactly what we see in this example. If you make one have less cardinality than the other, cardinality I should say, either you will fail onto or you will fail 1-to-1 like this.